Hello, and welcome to the second live session at the second annual Automotive Technologies Virtual Conference, produced by Embedded Computing Design. My name is Rich Nass, and I will be your moderator for this session and many of the other sessions that hopefully you'll be attending. I'm also the Executive Vice President of Open Systems Media. I lead the embedded IoT teams for Embedded Computing Design. The session you are attending right now is titled, What Comprises an Autonomous Drive Platform? This is clearly a very popular one, judging by the number of people that we have in the audience. Before we start, I'd like to thank our sponsors who make events like this possible. They are NI, the Crystal Group, DSpace, Acronix, NXP, Silicon Motion, Texas Instruments, NVIDIA, and Rambus. You may also know that at the end of this session, we're going to announce the name of one audience member who will win a SparkFun JetBot AI Kit 3.0, along with an NVIDIA Jetson Nano 2 gigabyte development kit that's needed to operate it. So stick around to the end when we announce the winner. As I said, this is the second of many sessions today. After this one, we'll be talking about the capabilities of modern ADAS systems and what's needed to design them. After that, we have in-vehicle infotainment, followed by how to power your EV. And we'll close with a session on how to keep your modern vehicle safe from hackers. If you can't attend live, all the sessions will be available shortly in an on-demand format. And that's along with about a dozen complimentary sessions on similar topics, all delivered by industry experts. But let's get to the topic at hand, where we will cover how to design and implement an autonomous drive system. We will have 4 speakers here. They are Colin Alexander, a director at Acronix, Steve Shi, a program manager at Silicon Motion, Stefan Gordon, a business development manager for ADAS and autonomous drive at DSpace, and Micah Snodgrass, a technical director for the Crystal Group. Before I bring out Colin to start things off, let me go over some of the housekeeping items. This entire presentation will take roughly 45 minutes, give or take a few, and that'll leave us some time to answer your questions, and we will get to as many as time permits. You'll find on the right-hand side of your console window an area where you can enter your questions in real time. As I said, we'll address as many as we have time for when the 4 speakers are done. If we don't have a chance to answer your question, someone from one of the 4 speaking companies will get back to you after we're done here. And for that reason, I encourage you to ask your questions as you think of them. Don't wait for the Q&A period, because we tend to answer them in the order that we receive them. If you have a question pertaining to the eCast operation itself, like if the slides aren't advancing or there's a problem with the audio, put that into the question box, and one of our technicians will get back to you with a fix. There's also a button over there on the right side that says handouts. If you click on that, you'll find a copy of the presentations that the speakers are going through here. And as I said, this session will be available in an archive version shortly after we sign off. So if you missed something, you want to go back and review, it'll be there for you. Okay, enough from me. All yours, Colin. Take it away.
Hello, everybody. My name is Colin Alexander, and I'm the Director of Product Marketing here at Acronix. As part of this segment of what comprises an automated drive platform, I'd like to take some time to look at the Fpga usage and designs for next generation autonomous vehicles. And in particular, take a look at some of the ADAS applications and how this is setting the need for further performance and integration in next generation designs. Today, I'm going to talk about these critical building blocks which will enable these next generation platforms. As a brief introduction, Acronix is a fabless semiconductor company. We've been producing both high performance and embedded Fpga IP for the last decade. And we're uniquely positioned within the industry as the only Fpga company which has both these technologies, both standalone FPGAs as well as embedded Fpga in high volume production. And in Acronix, we consider that embedded Fpga technology is an ideal element in the toolbox for accelerating many of these workloads in the car. So FPGAs have been widely used in automotive applications for well over a decade. There are over 250 million FPGAs in cars today, and in excess of 75 million of these in production in ADAS applications. Why FPGAs? Well, they provide a significant value in workload acceleration, where performance and latency are critical. The programmable nature of FPGAs allow them to address complex algorithms that require high-speed parallel processing capabilities. Additionally, in space and power-constrained environments, FPGAs offer the best performance per watt for accelerating workloads compared to running these on more general-purpose CPU or GPU-based platforms. Increasingly, with the move towards EV and with higher levels of autonomy needed, automotive designers need a platform to support the flexibility to meet changes in the rapidly evolving specifications. Cars today are pretty much becoming data centers on wheels. The need to be able to securely aggregate information from multiple different sensors, LiDAR, radar, or cameras, and then process these streams using AI or ML algorithms increases the compute performance required quite dramatically. Just as in data centers, one can no longer just add additional CPU compute power alone, and the same is true in a car. Further evolution of platforms to support the integration of CPU and the ability for workload acceleration for sensor fusion and ML processing in heterogeneous platforms to handle these accelerated workloads is needed. Therefore, we believe the next big technology trend is to combine the benefits of FPGA technology with the ability for designers to develop custom hardware accelerators that can be tightly coupled with CPU-based systems. This advance makes a very attractive value proposition to replace standalone FPGAs with embedded FPGA integrated in multi-chip module or ASIC designs to achieve significant cost, power, and space savings. Here we list some examples of applications today that are using standalone FPGAs, both in development and production. Advanced driver assistance systems are driving the need for aggregation of several capabilities into one platform for workload aggregation. A great example is the system announced by Continental last year with the ARS 540 radar module. They have developed this platform in conjunction with AMD Xilinx using the MP-SOC UltraScale standalone FPGA platform. The system is initially targeted at level 2 autonomy, but is intended to scale towards full level 5 capability in the future. The system is intended to support 4D radar technology. This is a new technology that allows for the capture and processing of high resolution detail for object identification in any lighting or weather conditions and at higher speeds. 4D radar can determine and track an object's range, distance, azimuth, direction, or even elevation, as well as its relative speed, whereas previous generation radar could only determine speed and azimuth. This system allows for higher levels of autonomy to be met in this platform and for future features to be added through time. The combination of radar, LiDAR, and cameras in a true sensor fusion environment helps in complex driving situations where smaller objects like pedestrians or motorcyclists may be masked by larger objects like trucks or other obstructions. As you can see here, looking at the list of examples, applications of where FPGAs are used are wide and varied. But for reasons of time, I'll not go into each of these in detail just now. Just suffice notice the reasons why FPGAs have been selected as listed here. However, as the systems evolve, there will be a greater need to balance the advantages of FPGAs with both cost and power reduction together with higher performance. That is why using embedded FPGA IP has started to gain traction in designs for the automotive market. So, motivation to adopt eFPGA IP in automotive ASICs. Over the past several years, there's been a desire for automotive manufacturers to develop custom chips to differentiate, particularly in their ADAS offerings. Tesla, for example, has taken this approach and developed their own full self-driving ASIC called the FSD ASIC. An image of the resultant board utilizing the FSD device is shown on the slide. This approach has allowed them to significantly differentiate their solution by creating an ASIC which has all the right amount of processing capability needed. However, this balancing process of designing their own SoC is challenging. As with any ASIC design, they're forced to define the specification years in advance of deployment, and therefore they face a risk that things may change in time before the vehicle is in production. For example, with the introduction of AI ML capabilities into designs, the algorithms are changing at such a rapid pace. There is a need to ensure that the state-of-the-art inferencing schemes are supported by the time of production, or even for over-the-air deployments through the lifetime of the vehicle. So the ever-changing nature of AI ML is one of the drivers behind the need for Efpga adoption. But by using Efpga IP, not only can you adapt the changing algorithms, but you can also significantly reduce the unit cost and power for over standalone FPGAs. Our estimates show that Efpga integration provides designers with up to 90% cost savings compared with standalone FPGAs, faster time to market, and extended product life cycles. An Efpga implementation allows for up to 75% reduction of FPGA power by eliminating unused resources and peripheral I/O in standalone FPGAs. Also, by integrating the ASIC and the FPGA monolithically, designers can achieve a 10x increase in the interface bandwidth between the Efpga and other system components. Finally, this integration increases the reliability by reducing the number of components on the actual PCB. And Efpga is already a mature technology. SoC ASICs utilizing Acronix-based Efpga technology have already shipped in excess of 10 million units into various segments. And Acronix have their first, at this stage, unannounced Tier 1 OEM customer who is using Efpga capability on a SoC specifically targeting supporting sensor fusion functionality for a high level of autonomy. As we continue to look at the benefits of Efpga, one of the main motivations to adopt IP is not only to support lower costs of deployment and to provide a platform for differentiation, but also to support extended product life cycles. The black line in this curve demonstrates a standard ASIC product life cycle. The green line shows that by including Efpga IP, you can extend the ASIC lifetime in the market by enabling earlier tape-out, support more product variants, and extend the product life cycle, which translates into increased revenue and market opportunity. Designers can accelerate availability of new platforms by taping out new architectures based on a new SoC earlier. They do this by partitioning the parts of the design that might change into an Efpga tile. This allows the designers then to incorporate support for the evolution of specifications, new algorithms, etc., without having to respin the ASIC. Additionally, the designer can simply reprogram the Efpga to support the latest changes after the ASIC is in production or is in the field. So as you can see by this slide, there's significant benefits to be gained in using Efpgas in SoC designs. So what exactly is embedded Fpga and how does it work? An embedded Fpga is a licensable ASIC IP core that can be embedded in just about any other IP core as well into any particular ASIC. The Efpga IP block illustrated is a typical example. It contains resources that mix the following: a user-defined amount of programmable Fpga logic or fabric, DSP and/or machine learning processing machine learning processor blocks, which provided dedicated high-performance mathematical operations and support various different floating point, block floating point, and integer number formats. And a fabric interconnect structure. We have what we call the 2D NOC that provides a high bandwidth connectivity between the heterogeneous functions on the SoC, CPUs, peripherals, memory, and I/O, together with the fabric. This interconnect enables a number of very important benefits in optimizing designs and supports the ability to dynamically reconfigure the fabric in real time. The mix of functions on the SoC can support multiple capabilities that ensures resources perfectly match the requirements of the emerging ADAS requirements. The Fpga can be tightly coupled with the CPU subsystem, utilizing off-the-shelf ARM or RISC-V system resources, meaning the eFPGA and subsystem can utilize cache and memory coherency capabilities on the SoC. Unlike standalone FPGAs, designers are not limited to the predefined configurations of the FPGA, and instead are able to make the exact amount of resources required for their application. As a result, all the external interfaces expected from standalone FPGAs can be removed from the system, thus optimizing performance and power consumption figures. Acronic's eFPGA IP is called SpeedCore. Once again, the eFPGA IP resource mix and I/O interfaces are defined for the customer. Acronics add this target device to our standard software tools, so it appears as a new FPGA design option. This is the same as the standard FPGA flow, so it's very easy for FPGA designers to design, program, and debug their eFPGA IP. Just a quick overview of eFPGA IP applications in an ADAS system. This diagram illustrates the different sensor fusion functions, how data can be aggregated into the fabric, and how it can be accommodated within custom ASICs and combined with different CPU subsystems. So here is a block diagram showing the different applications that can be accelerated in embedded FPGA IP in an automotive environment. The eFPGA can be used to offload other CPU, analog front-end, and dedicated ASIC accelerators. It can be designed to support shared memory and coherency schemes for efficient use of SoC resources. Specifically, one or more eFPGA tiles can be used on a SoC to support efficient, low-latency workload acceleration of multiple tasks. Each eFPGA tile could support various workload accelerators. So, for example, acquisition of multiple high-resolution camera, LiDAR, and radar sensor streams, perform tailored sensor fusion algorithms utilizing its embedded DSP engines or tightly coupled coefficient memory, can be used to format and align disparate data streams that can support video pre-processing for functions like edge detection and feature extraction, and can support real-time machine learning inferencing functions based on its hardened machine learning compute engines within the fabric, based to run, for example, MATLAB models on a pre-trained TensorFlow network. And the FPGA can incorporate custom crypto algorithms to increase the vehicle security and prevent unauthorized access to the ADAS ECU, for example, by locking portions of the fabric. So the designer can choose to create one or more types of custom data accelerators, as I've listed, inside the eFPGA, which then can be populated all at the same time, or depending on the resources available, by utilizing dynamic reprogrammability, programmed individually, and then allocated on a real-time as needed basis. So these are just a few examples of how you can use eFPGA IP in your automotive design. The flexible nature of an eFPGA allows for multiple deployment options and provides the ability to differentiate systems versus those built using standard off-the-shelf components. So in summary, as you've seen, FPGAs are already being used today in many mainstream automotive applications and for a wide variety of use cases. In particular, they have found great success in ADAS applications due to the rapidly evolving nature of these applications and the need for more and more processing performance. The evolution of ADAS designs will have a focus on migrating many of the discrete FPGA functions into embedded FPGA IP, which allows for much lower cost, power, and increased performance compared to standalone FPGA solutions. So it's been an overview, very short overview presentation, covered a wide variety of topics at a high level, and I'll pass this on. Thank you.
Hi, everyone. Welcome to the Automotive Virtual Conference. I'm Steve Shi, the project manager for automotive products from Silicon Motion. Today, I'm going to introduce the advanced storage for automotive applications. The automotive industry is rapidly transforming with technology-driven innovation, automotive standard shaping requirements, and consumer preference changing demands. More and more functions and applications are built in the automobile to fulfill the rapidly transforming for the automotive technologies. For the autonomous driving technology, it also changes very fast from the partial driving to full driving automotive in the future. So the electronic content becomes a bigger and bigger part of the vehicle. The storage technology is also growing to fulfill each technologies and applications shows us below and before. In the beginning, we have the road name in the car. And then there's a SD card to put the map and some other things in the car. And then we have eMMC and UFS for better performance and also the capacities. And now we have the PCI storage for the fastest storage and for all the applications that we're showing in here. And each of the NAND storage technology has their own job to support various applications in the automobile. For example, the autonomous car, the telematics, IVI system, drive recorder, DMS, and the in-vehicle computer, and also the ADAS system. So we have various storage to put in the car for each applications. The SD card only has low speed and low densities, but they have easier to insert or remove it, so it can be supported on map and dashboard cameras. For the eMMC and UFS, we provide better performance and capacities for basic functions in the automotive field, such as IVI and cluster. For the applications that need faster performance and high capacities, we offer PCIe BGA SSD for the ADAS and autonomous drive. From the research in 2025, the average autonomous vehicle will be generated from 5 terabytes to more than 20 terabytes data each day by day. So here is the question. How can NAND storage solution provider join this evolution? For autonomous driving in the future, the demand for fast and high capacity storage drives the development of embedded products. At this time, a higher end transmission system and a larger storage unit will be required. So there is a new architecture which called centralized system is coming for this revolution in the automotive. In before, the design concept in automotive was conventional architecture. It means there was a lot of application and the features separately built in a car. And it also required a lot of units to control them. But now, for the centralized system, we only need one or field systems to control all the features and applications. So it can save the cost, and also the applications can be defined and changed by software. So SRIOV PCIe drive become the key for the centralized system. So what is SRIOV and why it can be benefit the centralized system? Because it can allow one storage to directly support multiple applications. And why SRV can do that? Let me give you an easy architecture for it. So in current architecture, we'll need a hypervisor to schedule and request from each virtual functions. It will cause in high latency and low performance for each virtual machines. But in SRIOV, you can simply think about it. So in PCIe SRV drive, it will not need any hypervisor for it. The SSD has built-in virtual functions for each virtual machines. So each virtual machine can directly connect to each virtual function without delay or any performance drop. That is why the SRV PCIe drive become very important in the future, and it's one of the key for centralized system. After talking about the marketing trend for automotive storage, there is one more thing to talk, and this is also the most important thing in automotive field. It is safety, reliability, and quality. SMI's solution offering all the key items to the automotive quality requirements. For the temperature, we provide extended temperature and voltage for our products, which is also certified by AEC-Q 100 Grade 2 and Grade 3. And we offer good traceability to track back all the parts that we ship out to the field, to have a good quality for all the paths from manufacturing to the mass production. And for the data paths, SMI offering end-to-end data path protection to protect all the data from the host to the drive. And we also have SRAM ECC for SRAM soft or heartbeat errors to make sure the data integrity. And SMI offering better process control and scrap criteria, and document all the process and the flow to ensure the data integrity. In the design phase or after mass production, SMI also offering the failure analysis for all the products. In order to meet automotive quality, we have several qualification and certification for it. As I mentioned before, all of our product has AEC-Q 100 certified with the Grade 2 and Grade 3. And we also has SBIS certification, which means our process flow is following the SBIS rules. For the certifications, we have IATF 16949 compliance. So it means our product has passed the automotive process. And in order to meet the safety requirement for each applications, we also implement the ISO 26262 for the safety levels. For automotive grade controllers, SMI offering SSD controller, eMMC, and also UFS for each applications and features. And we also have SRIOV support on our PCIe controller. And all the controller is passing the AEC-Q 100 Grade 2 and Grade 3. So for the automotive grade single chip solution, we also offering Ferrite, SSD, UFS, and eMMC. So each of them is also passing the AEC-Q 100 certified for the Grade 2 and the Grade 3. At the end, I will give you the summary for the automotive storage and the slides that I showed on today. For the autonomous vehicles, we'll continue to drive innovation in flash technology to meet the performance and the capacity requirements, which is up to 5 TB. For the autonomous driving they require the reliable protection of the data, which is the end-to-end data protection. And for the SRIOV, the NVMe sharing can be a cost-efficiency way to implement the centralized system in the autonomous vehicles. For the function safety and the security, these are the key elements of the autonomous driving applications. And the Silicon Motion's automotive storage solution provides various storage to support different applications in the automotive field. If you have more questions or information that you want to know, please feel free to contact us through the website or the email. Thank you.
All right, good morning, everyone. Thanks for having me at the virtual conference here. So my name is Stefan Gordon. I'm with DSpace as a business development manager for ADAS and autonomous driving topics, based out of our Silicon Valley office in San Jose. If you would like to connect with me afterwards, the last name makes it pretty easy to find me on LinkedIn. So the title of my talk today is Why Simulation is Key to Autonomous Driving. And this seems to be a pretty bold statement, so let me explain how I come to that conclusion. To understand the solution, we probably need to understand the challenges first. And to understand the challenges, in 2021, Automotive IQ published a white paper where they surveyed 600 industry professionals, and they were asking the question, struggling to advance the slide. All right. So they were asking the question, what is your biggest concern in automotive software and technology development today? And the top answer was safety. And first of all, I'm happy that most of the industry professionals put safety as the number one concern in development, of course. So this comprises functional safety like ISO 26262 requirements, but also just in general, bringing platforms on the road that are safe to operate in public. Still struggling. I have clicked on the browser window. Okay, so second one is security. How do I prevent that someone breaks into my system? But not just someone breaking into the system. It's also the option to trick or fool the system, like with what it's called adversarial attacks. So in this example, we see clearly a limit sign with 35 miles an hour of speed limit. But in a published white paper from McAfee, they managed with simple modifications to trick a system from the Tesla Model X in this example to mistaken it as an 85 mile per hour speed limit. Yeah, next up is quality. So of course it's important to have high quality if you develop an autonomous driving system. This includes coding best practices, of course, but 30% of the people also answered the testing methods. The testing methods they have in place aren't exhaustive, which means they do not have capacities to test everything that they want to test, and they simply do not have time to test more. Yeah, next up, so of course, testing is important for safety and quality, but testing even has its own spot on the list. So next point is testing itself. From the survey, 45%, so nearly every one out of two people were answering they are struggling to test efficiently. So testing and software development are time consuming. And roughly 25% were also mentioning they're not testing early enough in the development cycle, so they find bugs simply too late. All right, I think now we switch to PDF, so now I can advance the slides myself. This will probably help. Okay. So first, the fifth one on the list is actually team productivity, where a lack of alignment between different teams was mentioned, but also it was also mentioned that QA cycles are just too long, and they are oftentimes simply waiting too long for the testing to be complete. So all of these have in common safety, security, testing itself, and team productivity with these answers, that they can all be addressed by testing and validation. So testing and validation can help with all of these concerns. Question is, of course, what if we speak about an autonomous system, what options do we even have for testing and validation? And the first one that comes to mind is, of course, real-world testing. So taking the system out on the road and test it in the real world. The advantages are, of course, it's closest to the production system, and the actual hardware and software are involved. You could say it's pretty much the ultimate test, of course. But the downsides are, of course, it's very time consuming and super cost intensive, and you can only test what you encounter in the real world, so you're pretty much limited in terms of test cases. And addressing the concern of not testing early enough, it's pretty hard or even impossible to test in the real world in early stages of the development. Another testing approach that tries to encounter these downsides is data replay testing. So in data replay testing, you have your sensor suite, for example, equip it to the vehicle with a test driver. You can drive around, collect the data, store it in a database, and later on, you can always reuse the data that you've once recorded. You can replay it to different kinds of system under tests and use it across different test cases. So the advantages are the input data should resemble the production system, at least if you record with the proper sensor suite. And the recorded data can always be reused for all kinds of different test cases later on, once it is recorded. The downsides are the data must be recorded and annotated first. So it's once again pretty time and also cost intensive. With the data replay approach, you can only do open loop testing. So you can only replay the data that you have recorded, but you cannot act on this data from your system. So if you recorded something where you're driving on the right lane, your system under test cannot invoke a lane change to the left lane, of course, because it's ultimately just a recording. Yeah, and the test cases are, of course, once again, limited to the existing recordings. You can only test what you've recorded before. So the third option that now comes into play that helps with the downsides of the first two ones is simulation-based testing. So testing the system in a simulation. The advantages are, first, it can be used in basically all stages of the development, and that means it can also be used in very early stages of the development. even when the hardware is not available. So this holds true for the sensor hardware, for example, but also for the compute hardware. So even then, you can still start to develop your autonomous driving system and test it in a simulation environment. For example, with simulated sensors and simulated vehicle dynamics and powertrain. This even helps to guide the overall system design process, because you do not have to select the sensors first and then build a system that can somehow cope with the sensors, but you can really focus on designing the systems, check in simulation which kind of sensors, which kind of sensor combinations work well with your system. And if you notice that a front radar with just 500 meters is not enough for your system to operate safely, you can simulate one with 800 meters. And if that's enough, you can probably go for that option in the real world later on. Yeah, it can be used in different use cases, like, for example, on a single PC. Function developer could use simulation environment to develop his functions, but it can also be scaled into the cloud to reach a broad test coverage, for example, if you have a lot of tests that need to be covered. Or it can also later on, in a later stage of the development, used in a hardware-in-the-loop system where you connect the actual ECU via the electrical interfaces to the simulation, and test it there. Second big advantage is it allows testing of corner cases. So we mentioned before that if you do data replay or real-world testing, you're limited to what happens in the real world or in your data logging test drive. In simulation, like we see here in the screenshot, you can artificially create situations that are probably difficult in real life. So like this accident situation with the truck here, or also situations that are very rare or hard to encounter in real life at all. So in this screenshot taken from a simulation, we see entering a group of animals entering highway situation at night. This is probably something that is very, very hard to encounter in a data logging drive. But of course, it's not something that's completely impossible. So you probably want to test your autonomous system against those corner cases. Next up, failure injection. So the simulation allows to artificially inject failures into the system, and you can see how does my system cope when there is a failure in the system. In the example, we see an image taken from simulation without any failures, but we also see how the system performs if there's a crack in the lens, if there's dirt or dust or something that is preventing proper operation. And this can also be used for the adversarial attacks that we've seen in the beginning of the slides for security testing. So you can artificially try to fool the vision system of the autonomous vehicle. And of course, you can test under various weather or environmental conditions like we see in this screenshot. Of course, you can also take out your real vehicle under different conditions, but then you still have to wait until the conditions are fine, and you can probably get some rain or fog. But in simulation, you can truly test all kinds of levels of fog, densities of rain, can artificially position the sun, and things like that. So you can really in detail test under those environmental conditions. Another benefit of simulation is it scales very well. So if you have a look at this simple example from the slide where we have a cut-in maneuver where the ego vehicle is driving on a lane and another vehicle is cutting into this lane, you can easily, from this logical test description, create thousands of concrete tests by creating different permutations, changing the ego speed, changing the speed of the fellow vehicle, or changing the distance where the cut-in is happening. And you can not only create thousands of tests, you can also simulate these and test them in parallel and not just sequentially. So this addresses the concern from the beginning to have not enough time and not a dense and exhaustive test coverage. Another benefit compared to the data replay testing is simulation, at least if you have proper simulation tooling, of course, allows closed loop testing. So you can simulate, for example, the input side of things, sensors like camera, radar, LiDAR output, or also GPS, IMU, and so on. And you can feed that data into the perception stack of your system and test detections, data fusion, localization. But with simulation, you can also simulate the vehicle dynamics, the powertrain, the motion control interfaces of the vehicle. And with that, you can also take driving functions into the loop, testing prediction, motion planning, and motion control. So if you're developing an emergency brake, you probably also want to know not just if the perception is detecting something in front of the car, but also if the driving function can really lead the vehicle to a safe stop and avoid a crash, for example. Yeah, and last but not least, simulation can also provide accurate ground truth data, basically at no cost. So if you have a data logging approach, you typically collect the data and then in a more or less automated fashion, in the end, still humans need to label the data to have ground truth, whereas in simulation, the simulator can directly provide a very accurate ground truth information. Yeah, and these are basically just the opportunities of simulation for validation and testing, but there are of course many more, and now simulation is even adopted also for the development itself, but that's probably a topic for the next talk. So thanks for the attention.
All right. Thank you all for attending this presentation, and I would like to thank the host who set this all up. It's a wonderful thing to be able to talk to folks all around the world. I did warn them when we were preparing this presentation that one of the big dangers, not just in autonomous vehicles, but in all sorts of presentations, webinars, panel discussions, is handing a microphone to an engineer and then giving them a topic that they love and they're passionate about. You'll get a lot of excitement and energy, and you'll get 3 hours of words that some people may care about, not. And so my partners in crime here have threatened to keep me on the straight and narrow here, and we'll go through this presentation as quickly as reasonably possible. I'm here to talk to you today about some of the concerns, requirements, and critical aspects in the hardware portion of autonomous driving. The earlier presentation, the Acronics presentation that Colin did regarding Fpga, he made a very, very good comment describing autonomous vehicles as data centers on wheels. And he referenced the ever-changing nature of AI and machine learning, and he is spot on those. And the solution that they're presenting is a very good end goal. The challenges that I'll be describing here and some of the answers to those challenges are generally implemented a step before the Fpga process. So the folks who are implementing Fpgas, they're further towards that end goal than what some of the rugged COTS or the data center type of solutions are targeting. So there's a logical progression in the hardware development. This is a very dynamic, changing market. One of the things that became very evident early on when technology first started being used with autonomous vehicles was that there is no one answer. Nobody is playing nicely with each other. Nobody is sharing information. Nobody really wants to collaborate together very much. You see some partnerships, and you see some companies consuming or buying or merging with other companies. And part of that is just the nature of the market. There are some very unique operational needs and requirements in this market, and there are also some unique challenges. This collection of needs and challenges is not something that any other industries have had to face on this sort of a development schedule. The extreme amount of processing power that's necessary has been developed. It is a development cycle that there are some very large technology companies working on, and they've been developing high-end processing capabilities for the data center for decades. The zero latency need, or near zero latency need, for communications on the vehicle is a technology that exists in data centers and in stable environments. The safety aspects are very critical, and those safety concerns have been addressed in low-powered solutions for cars and in high-powered solutions that are not in mobile platforms. So there's a collection of needs here that need to be met that are still early on in the overall life cycle of this industry. Part of the development challenge that we're seeing with companies who are leaning forward and trying to be the first to market in their particular niche is that the COTS components that are quickly available, that have the highest power available for computing and processing the data that's being ingested, those components weren't necessarily designed for an automotive market, but they're readily available. So a lot of software development teams jump to that immediately because it's easy to develop for, it's quick to get your hands on hardware. The big data center manufacturers have ensured that the technology, the hardware that's needed to do the really hard math is purchasable right now, today. Taking that and integrating it into a vehicle as a test platform and as a next step of the development cycle is crucial. And it's until the code is mature and you can implement it in an Fpga or an ASIC manner, there's a lot of testing that needs to be done and a lot of consideration that needs to be given. The ultimate goal, one of the big goals for COTS solutions in vehicles is leveraging the extreme processing power that's available from companies like NVIDIA, Intel, AMD, the various players that make the chips that most of the software at some stage is being written for. And once the software has been written for a COTS platform, it is often then moved off to a more targeted hardware platform. But in order to be able to take that step and use COTS processing hardware, the highest end processing hardware out there that's readily available, there are two barriers or two roadblocks that end up slowing down development and throwing a curveball for a lot of software development teams, as well as the integration teams that are responsible for putting hardware solutions on vehicles. One is just the nature of data center class computers. Data center class computers are not designed to go into harsh environments. They are intended for a nice, climate controlled, easily contained sort of environment that has a staff that looks after it and cares for it, and often has entire secondary buildings dedicated to keeping the hardware running in a reliable manner at room temperature with no abuse. Another roadblock that is often a showstopper or a impediment to the development cycle is heat management. The data center class components that are being leveraged right now by half the autonomous companies out there were not specifically designed to run on vehicles. That is a goal that the entire industry needs to get to, is automotive grade solutions that were intended for vehicles. But at this point, there are still a number of configurations and setups and vehicles out there that are using data center class components to validate their software and to test out their algorithms, to find bugs and make improvements. In order to be able to do that, the heat has to be managed, and it can't be managed using the default approach that data centers have been using for years. So we have to physically make these solutions more robust, and we have to deal with the heat in some manner. Neither of those two hurdles can be effectively addressed after the fact. You can't band-aid on design improvements. You can't just scab on a little extra quality and call it good. So there's a need for designed from scratch from the very beginning solutions that incorporate data center class components inside of shells, chassis, cases, configurations that are designed to handle the shock and vibration of being on-road, off-road, or out in the middle of nowhere construction sites, up in the air or even subsea, as well as solutions that can support the typical vehicle power bus. Another part of the headache that the industry is fighting with is that alternator power is not good, clean power, and data centers have nice, clean AC power that does not require high durability power supplies to run the equipment. Thermal management is also critical because electronics hate heat. Heat is the destroyer of electronics, and a very big kudos goes out to the design teams out there doing the hardware design on high temp components. That is very important, but it's a problem that needs to be solved from both ends. The higher temp components are important, and then also managing the heat, pulling it away from those components and dumping it outside the vehicle, not just in the cabin of the vehicle with the safety driver, or if you're up to level 5 with no other driver, you need to get the heat actually away from the parts and outside the vehicle. And this is best handled by a design that incorporates thermal management from the very beginning. Taking a data center class solution and then trying to effectively cool it aftermarket after the design has been completed doesn't work very well. We've done a number of case studies, and we've partnered with many companies over the years, the last 5-6 years in this field, and we've noticed a couple of things. One is that the solution is always changing. There is no one size fits all. There is no solve this problem and now you have the solution for the next 20 years. That doesn't exist in this industry. And any manufacturer that takes a vending machine approach to their customers, put a quarter in and get your product out, standard default product, finds that just doesn't work. Every solution's a custom one, and the integrators that are doing the deployment in the vehicles are very open to collaborative design. They know that that there are a number of roadblocks and a number of problems that need to be solved, and are looking for suppliers, companies, partners that are willing to step in there and work with them and go back and forth, not just try to force one particular configuration down their throat. I said at the beginning of the presentation that solutions like Fpgs and ASICs are the ultimate end goal, and I stand by that. That really is where the solution is going to be ending up. But every company out there doing this is going down the same road with multiple milestones, multiple development cycles. They're all on the same road. They just can't acknowledge each other. They can't share information, and most of them are at different milestones. So the key to rapid development and getting from one milestone to the next, to the next, to the next is at a certain point in your development cycle, there is a need for ruggedized COTS. There's a need to get the data center servers out of the vehicles, get a next step solution into the vehicles, and then at that point, once the algorithms have been proven out, once you've logged your 100,000 safety miles, or in some cases a couple million safety miles, you can move on to the next generation of hardware platforms. And now I believe we're going to throw it back to Rich for some Q&A. I just can't let it in here talk too much, so Rich, it's all yours.
Excellent job, Micah. Let me just wait for everybody to come back. And we're almost out of time, but we have a few questions that I want to run past you guys. Hopefully you're all with us now. So let's see. Let's start with Acronix. What support do you have for FPGA-based ADAS applications?
Sure, thanks, Rich. Well, multiple really. We work, firstly, we work with multiple different partners to develop functional solutions for different areas of ADAS. So as I mentioned in the presentation, these include, for example, sensor fusion, where you've got acquisition of camera, radar, LiDAR streams, and also, for example, ML applications as well. So these streams of HD data arrive over many different protocols with different security features, and the Fpga provides a flexible, low latency source to manage these streams. And also, we can incorporate multiple different ML inferencing schemes, including, for example, RNN and CNN, etc. And then next phase, we would work to identify the likely resources that would be needed and how you could interface up to different SOC components like CPUs and memory and I/O. And finally, just to be brief, we've got our tool suite, so we can support any development of ADAS functions through synthesis, debug, and optimization tools. We've got our standalone FPGAs. We can use that and then transition these designs over to a much more highly optimized speed core eFPGA based design. So, and for the sake of time, I'll stop there.
Thank you. Okay, so let's send this one to Stefan. Do you think simulation-based testing will replace the other testing methods in the future?
No, actually, I don't think it will replace the other methods. So I think all these methods that I mentioned in the talk are very important fields of application, and actually, DSpace is even providing solutions for all kinds of these applications. So we have comprehensive solutions for data replay testing, for simulation-based testing, as I mentioned in the talk, and also solutions for in-vehicle prototyping, for example. I just think it will be the perfect complement to the other testing methods.
Excellent. Okay, Micah, this one's for you. What's the difference between using enterprise GPUs versus consumer GPUs?
We get a lot of requests from companies that are early on in their algorithm development to use consumer class GPUs because they're readily available and they're cheap. There's a price concern there. However, enterprise class GPUs are intended for constant usage. They incorporate data corruption protection, ECC memory, and several other features that allow them to run 24/7 around the clock rather than just the periodic, temporary, non-critical usage that the consumer solutions were designed for.
Excellent. And we have a similar question, Steve, for you. And I'm paraphrasing for the person, what's the difference between memory that's intended for automotive applications versus memory that's just general purpose memory?
Okay, so I think for the functional, it's not big difference. Maybe just one, and that I just have a presentation that is SIRV. Actually, that is already in the networking for a long time, but it's going to be in the car. And the others is like the quality and the quality certification that I mentioned before for the such as some ISO 26262 or some other safety logos, and also for the temperatures that can be done at the storage, like we can suffer around 105 degree and also down to the -40. So that is a big difference to the consumer product, because I think the consumer product just can be done for the 0 to the 70. Yeah. So I think the most important is the quality. Yeah.
Very good. Well, folks, I am afraid that that's all we have time for. I need to thank our sponsors one more time. They would be NI, the Crystal Group, DSpace, Acronics, NXP, Silicon Motion, Texas Instruments, NVIDIA, and Rambus. And as I said in the beginning, we have a door prize to give away, a SparkFun JetBot AI Kit version 3.0 that comes with an NVIDIA Jetson Nano 2 GB development kit. And the lucky winner is Eliza. Eliza, that would be you. I'm sorry, I take it back. I should have my glasses on when I do this. Letitia E. We will be reaching out to you to get your contact information so we could send that to you. Okay, so we are done here. We have lots of other sessions going on later in the day. We have a session on ADAS, electric vehicles and powertrain, in-vehicle infotainment, which includes vehicle networking and connectivity, and safety and security. So check those out. And thank you all for attending, and I hope you have a great day.